Hello, welcome to the video presentation of our TMLR submission, Interpreting Kolmogorov-Arnold Networks in Neuroimaging, a path-based attribution framework. In this work, we propose a new way to compute global feature attributions in Kahn architectures. We evaluate the framework in the neuroimaging domain, specifically on Alzheimer's MRI data, because this setting requires interpretability at voxel-level resolution. Deep learning methods have achieved strong performances across many applications in recent years, including medical imaging tasks such as Alzheimer's disease dissection from MRI scans. However, these models are often difficult to interpret due to their fixed nonlinearities and are commonly regarded as black boxes. In high-stakes settings such as medicine, it is not enough to achieve good performance alone. We must also understand why a model arrives at a particular decision. Clinicians need to relate model outputs to real-world data in order to gain meaningful insight from the patterns machine learning systems identify. Most existing attribution methods, such as gradient-based approaches and relevant propagation, produce local explanations. These explain individual predictions, but make it difficult to identify consistent patterns across a population. Global explanations offer additional advantages such as model debugging and the ability to verify that a model is relying on clinically meaningful features. We investigate neurodegenerative diseases such as Alzheimer's in this study, where structural changes occur across many subjects and show consistency across the patient population. This requires global attribution methods that can reveal patterns learned across the entire dataset. We also choose the neuroimaging domain because of its high-dimensional nature. Individual data items contain hundreds of thousands of voxels, making manual analysis infeasible. Some model paradigms are better suited for this kind of analysis than others, which brings us to Kolmogorov-Arnold networks. Our work builds on Kolmogorov-Arnold networks, or CANs. Unlike traditional neural networks that use scalar weights on edges, CANs place learnable univariate functions on each connection. Each edge function consists of a base activation component and a spline-based component with simple addition performed at the nodes. This structure allows the transformation from inputs to outputs to be represented as a composition of explicit functions, each of which can be analyzed individually. As a result, CANs provide a natural framework for studying how information flows to the network. However, existing approaches for CANs primarily focus on local edge importance and do not fully capture how information propagates to the network. We therefore propose a framework that considers the contribution of each edge within the path it lies in and across the entire network to score the influence of each input feature to the output. The first step in our framework is to compute an importance score for each edge function. Since each edge represents a function, its contribution depends on both its learned parameters and how it behaves under data activations. We can define edge importance using measures such as the norms of the base and spline components or other activation-based statistics. The example shown here is the L2 norm of the combined base and spline components of the edge function. These edge scores capture the local influence of each function, but they do not account for how this influence interacts with the rest of the network. Hence, we come to the path-based attribution approach proposed in this work. To capture downstream effects, instead of considering edges independently, we propagate edge scores along all paths from inputs to outputs. The importance of a path is computed as the product of edge scores along the path, with normalization applied to ensure stability, as seen with the tanh normalization. For a given input feature I, the attribution score is obtained by aggregating contributions from all paths originating from that input. This can be expressed as the attribution for input I equals the sum over all paths from input I to the output of the product of edge scores along each path. This formulation captures both local edge behavior and downstream interactions across the network, effectively measuring how information flows from each input to the output decision. While the path-based formulation is intuitive, explicitly enumerating all paths is computationally infeasible, since the number of paths grows exponentially with network depth. To address this, we derive an efficient matrix-based formulation. We represent edge importance at each layer as a matrix and compute input importance through chained matrix multiplication across layers. This produces the same result as path enumeration, but with linear complexity in the number of edges. This makes the method scalable to high-dimensional volumes, such as MRI data. We need such an approach as our initial problem was to analyze high-dimensional neuroimaging data. Visualized here is a card with only 128 inputs with a width of 20. We can see how mangled this network looks. But when working with deep cons or neuroimaging data, we need to scale up to hundreds and thousands of inputs with very wide and deep networks comprising millions of edges. Hence, we propose an approach that scales linearly with network depth and number of edges. We evaluate a framework on 3 neuroimaging datasets: OSS, ADNI, and Mendeley. Neuroimaging provides a challenging setting because MRI volumes are high-dimensional and meaningful interpretation requires identifying relevant structures at voxel-level attribution. By applying a framework to train Kahn models, we obtain global attribution maps that reflect the model's learned behavior across the dataset. To quantify performance, we use perturbation-based metrics such as insertion AUC, deletion AUC, and sufficiency, which measure how the model's predictive power changes as we modify the input. The proposed approach performs significantly better than prior works on 31 out of 36 baselines. So we can quantify the maps using perturbation metrics. But what do they actually look like when we visualize them? The resulting attribution maps highlight structured and consistent regions rather than noisy or scattered activations. When applied to neuroimaging data, the framework identifies regions known to be associated with Alzheimer's disease, including the corpus callosum, posterior and thalamic radiation, and areas in the prefrontal, parietal, and temporal cortex. These findings align with established neuroscience literature, suggesting the model is relying on biologically meaningful features. The L1 scoring approach, as seen in the original Kahn implementation, considers local edge contribution, but does not account for interaction with other edges or downstream effects, discounting any interaction that happens later on in the network. The Kahn 2.0 paper builds upon this. They compute edge scores recursively from the output node to the input node. Although they consider downstream effects, utilizing standard deviation can discount sustained activations. GAM relies on local explanations before arriving at a global explanation, making it computationally expensive as local explanations need to be calculated for the entire training data or testing data before the algorithm can be applied. Our framework analyzes the trained network itself to arrive at explanations as a property of the network. Hence, we do not require training data post hoc, and we can compute attributions without the need for excessive computation. So this is qualitative evidence. We need stronger validation that the framework accurately identifies known ground truth regions. To test this, we designed a synthetic experiment. A model is trained to distinguish between triangles with holes and triangles without holes, as seen with the label 1 and label 0 examples. The holes are always located in a predetermined region of the triangle, highlighted here in red. When we apply a framework to the trained model, the identified regions exactly match the ground truth hole region, visually validating the approach. With this simple validation done, how do we verify the framework on complex brain data? We apply it to a Kahn trained on the OSS1 3D SMRI dataset and overlay the Johns Hopkins white matter atlas and the Brainetom gray matter atlas onto the resulting global attribution map. Since all data and atlases are registered onto the MNI space, we can map each highlighted region back to a specific part of the brain. Here we see the primary regions identified as the body and genu of the corpus callosum, both of which are documented as relevant to Alzheimer's disease in literature. We also see bilateral posterior thalamic radiation, the prefrontal, parietal, temporal, and posterior cortex, among several others. This kind of validation supports the claim that a framework correctly identifies the features the model relies on and generates faithful global explanations. In summary, we propose a path-based attribution framework for Kolmogorov-Arnold networks that compute global feature importance by tracing information flow through the network. The method captures both local edge behavior and downstream interactions and can be computed efficiently using a matrix-based formulation. While we demonstrate the framework on neuroimaging, this approach can be applied more broadly to other domains where understanding feature contributions across a trained model is important. It is also important to know that while this framework identifies relevant inputs used by the model, its effectiveness is contingent on model performance. You cannot explain what the model has not learned. Therefore, attribution maps in medicine must be used alongside extensive evaluation and expert opinion, as they are not standalone evidence. These maps should be regarded as supplement to clinical data and not as a substitute. Therefore, we would like to thank the anonymous reviewers and the action editor for their valuable feedback, which has significantly improved the quality of this manuscript. We are grateful to Priyam De for his helpful input during revision and to K.S. Suryanarayan for his contribution to the figures. This work was also partially supported by MSTAR, the Pratiksha Trust extramural support for transformational aging brain research. Thank you for your time.